just let me run through this and I'll teach you the new concept, right? So I did mention how to do this one roughly, I think. Let's see how this done. Okay, they said hydrogen burn in oxygen. I'm going to do the working here. Okay, hydrogen. Okay, hydrogen burn in oxygen, right? Oxygen, and then it gives you water. Okay, quick one, huh? Alright, give you water, and then I mentioned that you are supposed to write ICF, right? So this is initial moles, change in the moles, and the final number of moles, right? So let's see how many moles of hydrogen do we have. Yeah, 0.1 grams of hydrogen. So I'm going to write down number moles of hydrogen is equals to 0.1 divided by 2. Okay, 2 is the MR of hydrogen, H2. So this gives you a value of 0.05 moles. Alright, so number moles of oxygen. Okay, number moles of oxygen, I think you have 3.2 grams. So 3.2 MR of oxygen is 32. Okay, yeah, so this gives you 0.1 mole. Alright, 0.1 mole. So we're going to fit everything in the table here. So hydrogen, I'm going to put down 0.05 moles. Oxygen, I put 0.1 moles. Alright, don't care about the water, I just put 0 here, but actually water is not important here. They're asking what is the pressure of the gas left behind. Water is a liquid, so we don't really bother about that. Maybe? Alright, so when they react, I hope you can see that oxygen actually is the one in excess, right? In excess. So all the hydrogen will react. So minus 0.05. Okay, 0.05 moles of hydrogen will be used up. And the reacting ratio is 2:1. Okay, can you see that? So if 0.05 moles of hydrogen is used up, I'm going to use half the value of half the moles of oxygen. So this one should be minus 0.0 what? 25. Good. Yeah, half of it, right? So the number moles of hydrogen water produced, you can see the ratio is 2 and here 2, so it's actually 1:1. Yeah. So the number moles of water produced is actually plus 0.05, but actually I don't care about the water, okay, because it's a liquid, so actually not important. All right, but I'm just writing that down. Okay, so eventually, let's see what's happening. So eventually you have no more hydrogen, and then you have 0.075 moles of oxygen, right? This one actually 0.05, but never mind, that's not important. We only care about the leftover gas. Okay, this is a leftover gas, and that's it. You can solve already using PV equals to nRT. So let's try putting PV equals nRT. So they're asking what's the pressure, right? So pressure, I don't know. The volume is 2 meter cube. Very good. Just is all meter cube already. So well done. So PV nRT, I'm just using PV equals to nRT. Right, just to make sure you understand that. So the number moles of gas left over is 0.075. Oxygen, R is 8.31, and then temperature is 20 degrees Celsius here. So 20 plus 273, temperature in Kelvin, yeah? So you can work it out, pressure, press your calculator. Okay, you get 91.3, okay? 91.3. Okay, and that will give you Pascal. Okay, make sense? Okay, so that's the idea. Okay, so let's now study the other part of gases. We'll look at how the graph looks, and we'll try to understand why does it look in this way. Okay, we'll try to understand why it looks in a certain way. Yeah. Okay, so let's go back to the basic. All right, let's go back basic. So I think in the beginning of for gases, right, when I started off. Okay, this one is fine. Okay, right, not difficult at all. Okay, so in the beginning, I mentioned about gases. So two very important concept for gases is over here. So all ideal gases have negligible volume. Ideal gases have negligible volume and negligible intermolecular forces of attraction. Is it okay? Is it for ideal gas, right? Ideal gas. So these are the properties or the assumptions for an ideal gas. So let me draw it out here. Then it'll make total sense. Let me just draw it out over here. Okay, let me look at which slide. Okay, let's try this slide here. So I'm gonna just they are asking you deviation from ideal gas behavior. So what kind of pressure and what kind of temperature will it not allow it to behave like an ideal gas? Okay, so let's try this. I'm gonna push this aside. Alright, okay, so I'm gonna just draw two pictures, and hopefully everything will make sense really. So this is like what I did last week. Okay, that's what I did last week. So I showed you a container with all these gases, and then I showed you a container with these gases, so just like that. Okay, so I mentioned that this one is which one ideal gas, 1 or 2? Which one is the ideal gas condition? Which one ideal gas? 2, yeah. Alright, this ideal gas. And I call this non-ideal. They either call it non-ideal or sometimes they just call it a real gas. Okay? Non-ideal gas or real gas. Alright, so let's think of in terms of the pressure and temperature. Okay, look over here, this one. This one should have high temperature, no, high pressure, low pressure. Look at this picture. Ideal gas will have low, right? Good. How about temperature? High, good. Anytime you can see molecules are very far apart, it must be high temperature. Because when you start to cool it down, they'll actually come closer and closer and closer, like liquid, gas to liquid to solid. So ideal gas, when the molecules are very far apart, is high temperature and low pressure. So non-ideal is of course the opposite. High pressure, like this case. Look at this picture, is high pressure, and also low temperature. Low temperature, the molecules will actually come closer and closer. So when does it deviate from ideal gas behavior? So when they say deviate from ideal gas behavior, then you have to look at here, alright? So it will deviate from ideal gas behavior at high pressure and low temperatures, okay? So let's look at the picture now, right? High pressure, low temperature. So let's see how they explain. So when does it deviate from ideal? They call it deviate from ideal gas behavior. Deviate, So at high pressure and low temperature. But you know, when you talk about high pressure, you have to write 2 points. But at low temperature, you write only 1 point. So high pressure, which is this picture here, look at this high pressure, right? We say just a very, very quick one. At high pressure, you must say the volume occupied by the molecules is significant compared to the volume of container. So volume of molecules is significant compared to volume of container, right? As you can see from here, very significant. And because they are very, very close, they are extremely close, we take it as the intermolecular force of attraction, right? Because they're very close, intermolecular force of attraction also becomes significant, okay, because they're very, very, very close. So they say the intermolecular force of attraction are not negligible. When I say not negligible, is taking the same meaning as significant, okay? Not negligible, so it's actually significant. Yeah, same concept. Alright, when I say not negligible, it's actually significant. So low temperature, which means the molecules again come closer. Gas very far away, liquid becomes closer, right? Then solid becomes even closer. Can you see that? So when they're very close, you must tell me the intermolecular force of attraction becomes very significant also, right? So actually very funny, but this is how we have to write it. When in terms of temperature, please talk about intermolecular force of attraction. But for at pressure, please talk about the volume and intermolecular force of attraction. So actually the focus, the truth is this, the focus at A level even, we always focus on intermolecular force of attraction. Okay, we're going to focus on it. I'm going to show you what I mean by that. We focus a lot on intermolecular force of attraction. Okay, so very quickly look at this graph now. Okay, let's look at this graph now. PV equals to nRT. I'm going to take a number of moles of gas. Number of moles of gas, take it to be 1. Okay, for this graph, take it to be 1. So if I use this formula, PV equals to nRT, I'm going to write down as PV over RT equals to N. Alright, but since I told you the number of moles of gas is 1, PV over RT is 1. Okay? Yeah. So this is ideal gas. So if an ideal gas, PV over RT must always be 1. So at 1, can you see this is ideal plot. Ideal plot means for ideal gas, theoretically the graph should look like this. But of course, not gases, all gases are not ideal. They tend to deviate from this ideal line. So can you see at this point, at high pressure, right? What do they say about high pressure? High pressure, it becomes a non-ideal, right? So you can see when it's non-ideal means at high pressure, it deviates from the ideal line. Okay, ideal line is just, so it's like deviating. Can you see that? It's going further and further away. And at low pressure, what happens? At low pressure, it becomes more ideal, right? So at low pressure, they come back to 1. So when it comes back to at low pressure, right, it comes back to 1. When it comes back to 1, it's ideal. Make sense? Yeah, so at high pressure, deviate. It's like going higher, right? Okay, how about temperature? Okay, temperature. If you look at temperature, this is how we look at it. The truth is this, I just want you to understand one thing. The truth is for A level, right, when the schools and the examiner mark, they only mark for deviation over here. Okay, they really only mark for deviation over here. So the one that deviate the most is the one that goes very far down. Okay, deviate. So we only mark here really. Over there we don't really mark already. So because that part can vary a little bit. So when it deviate the most, it goes further down and then goes further up. Okay, so it goes further down. So you're going to mark for the fact that it goes down. So look over here. Which one goes down the most? Look at it. Which one goes down the most? In fact, the one that goes down the most is the one with the, let's see, this one. This one goes down the most, right? Okay, look here. This one has the what? Lowest temperature here. So when it's at low temperature, it will deviate more. And when we look at deviation, greater deviation, we draw further down. Okay? Okay, this is a concept. So a lot of students don't understand this little concept. They always ask, why go down then go up? Right? Well, deviation, go down is deviation. Go up also deviation, isn't it? Go down is deviation because you are going away from this line. Then go up also deviation. So there's a little concept over here. This is the concept we're going to teach you why it goes down and then goes up. Okay, so maybe just for info, okay, I'm going to explain to you why go down and go up. Okay, so imagine I have a gas range, right? So say this. Okay, so this is a gas range. Actually, I brought a gas range, but I couldn't find one bigger one, so I had a very, very small one. Let me see if I have one. Oh yeah. Okay, so I have a gas range here. So imagine there's a gas. Actually, I have to use a very big one to illustrate, but sorry, I didn't have one big one. Okay, but this is what it means. If you have a gas range, initially when you press it down, okay, I think you all have had this experience before. If you cap it, right? You cap it, and then when you press it down, right? It's quite easy to press, right? It's quite easy to press in the beginning, but after some time, it gets very, very difficult to press, right? Okay, so there's a reason why in the beginning it's quite easy to press and compress, but up to a certain point, no matter how you do it, cannot really. Okay, so there's a reason why that happens. So actually, when molecules are quite far, I mean in this instance, right? Like I just draw like this. So there's actually significant intermolecular force attraction between them, right? If they are relatively close, there's actually significant intermolecular force attraction. So when you compress it, you look at PV. I'm going to focus my concept on PV only, all right? So when I increase the pressure, because of the significant intermolecular force attraction, right? The volume, okay, firstly the volume will drop. Is it okay? The volume will drop, right? But because the significant intermolecular force attraction, the molecules will be put even closer. You'll be put even closer. So what I'm trying to tell you is this. I increase pressure, you know something? The volume dropped, supposed to drop by so much, but it didn't drop by so much, it dropped even more than expected. Why does it drop even more? The volume dropped even more than expected. Why? Because they have significant what? Intermolecular, right? So because of significant intermolecular, the molecules come even closer and the volume drop even more. So when you multiply these two values together, what does it tell you? It will go up or down? It will go down, right? Yeah. So this whole area, why does it go down? The reason is because there is significant intermolecular force attraction. Okay? Now let's look why it goes up. Okay, why it goes up. So why does the graph goes up after some time? So the graph goes up only when at very, very what? High pressure, right? So imagine, I'm going to draw again. I think maybe some of you can tell already. So I'm going to compress until like up to here. See, I'll compress up to here. So I'm going to compress, no matter how I press, right? No matter how I press, it's very hard to compress anymore because the picture looks like this. This is the picture at very high pressure. Okay, this is the picture at very high pressure. Okay, this is a picture at very high pressure. So at very high pressure, I keep compressing, right? I increase the pressure by a lot. Okay, I increase the pressure by a lot. But actually the volume only dropped by how much? A lot or little? Because it's very hard to compress anymore, right? So no matter how I press very hard, but the volume may drop by very little. Okay, can you tell me why the volume dropped by little? What's the other assumption? So because at this point, what might you say? The volume is now significant. Okay, the volume, because all the gases occupy space, right? So you think easy to compress, isn't it? All the volume, all the molecules here occupy space. You want to compress, also very difficult to compress. Okay, because they all occupy space. Here got still so much empty space to push it, right? But by now it's quite significant. So volume is significant, which means no matter how you compress, the truth is the volume only dropped very little. So why does it go up? So now you know why it goes up. So it goes down, then up. So why does it go up? Go up because the volume of the molecules is significant. Why does it go down? Because the intermolecular force attraction is significant. That's why there's a down and there's an up. It's okay? So but we got to mark for this. So I told you, where do we mark? Actually at A level, we always mark for this part. So which factor must you always pay more close attention to? Intermolecular. Okay, you always pay more attention to intermolecular force of attraction. I mean, yeah, so that's how we're going to do it. Okay, so very quickly, if you look at this slide, you can probably see what I'm trying to say. Alright, you can probably see what I'm trying to say. Look at this slide here. Okay, for the marking point will be this part. See, I put a little box here, right? To show you that when I mark, I'm going to mark in this part. So I'm going to look focus 100% on the intermolecular. So ammonia has what kind intermolecular? Ammonia has what kind intermolecular? Hydrogen bond, because there's a H attached to a FON. There's an N there. It's a hydrogen bond, quite strong. Okay, hydrogen and nitrogen, what kind intermolecular? ID, because they're all non-polar. Good, non-polar. ID. So let's think through. Which one's stronger, ID? Nitrogen or hydrogen? Okay, ID is dependent on number of electrons. Good. So the one with more electrons has stronger ID, which means this ID will be stronger compared to this one. You mean? So look at the graph now. It's quite obvious that the strongest, the one that deviates the most, has the most significant intermolecular. This is the one that goes down a lot. Then followed by which one? Nitrogen. Okay. You notice hydrogen. Hydrogen is one of the rare ones that didn't go down. It only went like that. It's actually quite ideal. Okay, it's quite ideal. There are only two gases that if you want, you can draw up like that. No, without going down. There are only two gases. Take note, you want to draw like that, you can, but it only applies to hydrogen and helium. These are the two smallest atoms or molecules. Can you see that? If you want to draw going up, yes. In fact, these two are the ones that just goes like that. It doesn't even go down. Because quite ideal really. Intermolecular is quite negligible. Are you me? So you can actually draw quite ideal. Alright, so this is how it works. So if you look at it, that's how we're gonna mark. Alright. In fact, all what I mentioned here is actually explained over here, Ken. Yeah, so I didn't show this page, but that was what I was talking about. Okay. So the first part, intermolecular force of attraction, is significant. Second part, at high pressure, this is significant. At low pressure, this is significant. Okay, that's the concept. Alright, so actually it's all written down here. Ammonia has hydrogen bonding or hydrogen bonds, deviate the most. These two have weak ID, but nitrogen and ammonia have ID, but nitrogen has a larger molecular size and electron cloud, so the ID is larger. So you notice something? I didn't even talk about the volume, right? Yeah, but if you want to, you can still talk about volume, but volume only affects the later part. Okay, volume only affects the later part. But the truth is this. So I talked a bit about volume, but actually volume only affects the later part of the graph. So normally we don't mark for that. Okay, generally I say generally, you can't, it's not 100% all the time, but generally if it goes down more, it tends to go up more. But in this case it didn't. Okay, that's why it's hard to mark on this side. But what we mark is on this side. I mean, yeah, this part is very easy to see. But sometimes it goes up, goes down more, supposed to go up more. See, but this one didn't go up as much. But you know the previous graph I drew? Yeah, the previous graph is this one. See? This one went down more, right? Also went up more. And I know a lot of people say, hey, why cut all the same place? This is a coincidence. Okay? There's no significance here. I mean, this is a coincidence only, based on this graph. So students try to, after they draw, they want to cut all the same place. Sorry, no need to cut the same place. It's a coincidence. I mean, it's just a coincidence. Alright, okay, good. So with that, I think you might be able to do it. Alright, so are you me? So this is the concept for why the graph goes down and up. Alright? Okay, this concept, maybe just to show you what I mean by most easily liquefied by cooling and applying pressure. This statement tells you the gases have significant or negligible intermolecular force. Very easy to become a liquid. Very easy to become a liquid by cooling. So the intermolecular force attraction here must be what? Significant, negligible? Significant, negligible? Significant. Good. That's why it can become liquid so easily. Molecules come very close to each other very easily. Right? There's a very strong attraction. Okay, let's maybe run through the first slide since you're done already. The gas that likely to deviate most would have the most significant intermolecular force of attraction. So this one has ID, non-polar. This one also non-polar, has ID. This one, of course, ID, but this one is ID and PD. Can? Yeah, PD. This one is both, because this guy is polar, right? All the rest are non-polar. So definitely is A. I think this one is also quite simple because I hope you can tell that ammonia would have H bonding. Okay, the rest are all ID only. Alright, so H bonding over here, so it's D. Okay, let's look at how we sketch. Right, it's okay. Just look for the most significant intermolecular. This guy is H bonding ammonia. Right, the rest are ID. Okay, let's look over here. So I'm going to do the one for lower temperature first. So decreased temperature, when you lower temperature, the molecules come closer, would have significant intermolecular force of attraction. So this one will deviate more. Okay, this one will actually deviate more. Okay, deviate more. Alright, deviate more from the ideal gas behavior. So which means deviate more, I want to show you go further down. Alright, go further down. Maybe I just draw further up lah. Okay, so this is for part 2. Alright, for part 2. So the one that deviate less, increased temperature, the molecules are further apart, less negligible intermolecular force, will deviate less. So I guess I'm going to draw this one here. Okay, something like this, can? So this one. Make sense? Okay, 1 and 2 here. I mean, is it okay? Simple. Okay, this one for this question for helium. I think helium is the most ideal one. I told you helium and nitrogen. Okay, if you draw helium coming down a little bit, it's fine. But helium actually I can even draw like that. It's okay. This is helium. I mean, I told you helium and nitrogen didn't. Helium and hydrogen don't deviate a lot. Right? Doesn't deviate a lot. So it's just like that. Okay, ammonia deviate the most. Ammonia deviate the most because of the hydrogen bonds. I'll draw further down. Okay, so I just draw like that ammonia. I mean. Okay, but like I say, the marking point I only mark on this side. Okay, this part we don't really look already. Okay, carbon dioxide. Where's carbon dioxide? Actually, carbon dioxide is a nitrogen. Okay, we're gonna look at these two, carbon dioxide, nitrogen, because both of them are non-polar. Okay, carbon dioxide is linear. It's also non-polar, right? So they only have ID. So for ID, I'm going to just check about the number of electrons. So carbon is like 12.6, and then oxygen is 16.8. So which means the number of electrons on carbon would be 8 plus 8 plus 6, can? So that makes it 22 electrons. Because ID is only dependent on electrons. I'm counting electrons only. So N2 is 14.7. So if I count the number of electrons on N2, actually it's 14 electrons. So I guess this is how I look at it. Oh, more electrons, stronger, ID. So this one should deviate a little bit more. So I'm going to draw, use a different color. So it's somewhere in between what? Ammonia and nitrogen. Good. So somewhere in between ammonia and nitrogen. So I'm going to draw something like this. Okay, so this one I will take it as, so this one I'm going to write over here. The blue one is, okay, ammonia. Then this one is carbon dioxide. This nitrogen. And this one is helium. Okay, so it works this way. I mean, so just look on this left hand side, can already. Okay, you can see for this equation, this question, right? Gas X and gas Y. Actually, if I look at options, right? There's only 2 gases, hydrogen and sulfur dioxide. Okay, which gas is sulfur dioxide and which gas is hydrogen? Okay, sulfur dioxide is which gas? The one that deviate more, right? Yeah, the one that see the curve down. This one doesn't curve as much. So the one that deviate the most will have more significant intermolecular. I believe this one is SO2, alright, and then I believe this one is hydrogen, can deviate less really. So I can see from there, so X is SO2, and so I can eliminate a few already. Yeah, I can take away A and B already, right? Because I guess this should be, yeah, you can see the shape of the graph, is okay? Yeah, so I don't think this is hydrogen, it should be SO2 already. So I'll skip this to, yeah, so now I have a choice of between C and D, right? Between C and D. So, okay, the answer actually is, if you work it out, just go through the answer. The answer is actually D, C, sorry. The answer is actually C. Okay, I'll show you why the answer is C. PV is equals to nRT. All you need to calculate is nRT, right? So for C, let's try the nRT. For gas X, nRT will be 0.25 times R times T. T is 25 plus 273. Always must plus 273. Alright? Oops. Okay. Okay, this one here, for this one here, 0.5 times R, oh, same thing, 25 plus 273. Okay, so if actually this value here, if this was X, this one will be how many X? 2X, right? Because it's double, right? 0.25 is 0.5, right? So you can see that for gas X is X, gas Y is 2X, right? For gas X is X, and then for gas Y it will be double. Is it okay? Yeah, so I just put nRT can be. Make sense? Yeah, this value is double of this, right? Yeah, that's all. Okay, so that's how we look at it. Okay, this one here. Okay, this is more like I think this type of questions are quite popular then for a lot of school paper, right? But let's see what it really means. Okay, actually, this is the non-ideal gas. So ideal gas actually became PV. Okay, for ideal gas became PV equals to nRT. Alright, so very quickly, that is for non-ideal, this is for ideal. Alright, this is for ideal. So we have all these funny things here. What are these funny things over here? Right? What are these funny things over here? So I'm gonna just share with you. Actually, this V, you know when you use the word V, right? What's V actually? Volume of what? Yeah, this is very important. Volume of what? Yeah, actually V is the volume of the what? Container. So actually V is the volume at which the molecules are in, right? Okay, but the truth is this. Actually, V must be the volume of is the space that the molecules can move. V should be the space that the molecules can move. Okay, so theoretically, the V, if these are the molecules, right? Actually, V must be the space that the molecules can move. So actually, by right, V is supposed to be V of container minus V of the what? Volume of the what? Molecules. Yeah, actually by right it should be like this. But how did it end up to be V of the container? How did it end up to be that? Yeah, because volume of the molecules, you take it to be what? Negligible. It's okay. So this part actually we took it to be like 0, negligible. Alright, that's why we end up getting just PV. Okay, so actually if it's a non-ideal gas, you have to minus the volume of the molecules, right? Because you need to actually, the V really, this component is actually this space here, okay? Without, you must minus away the space of the molecules. I mean the green part, so you get what I'm trying to say lah. So you must minus, it's the space that the molecules can move. So you have to take away the volume that is being occupied by the molecules, yeah? So that's the idea. So actually the V is typically this space here that I'm talking about, right? So that's what I'm trying to tell you. Okay, so I hope you understand the concept. So what's the answer then? Yeah, the space occupied by the real molecules. So it became ideal when this was 0. Okay, it became ideal when this was 0. Okay, actually we put in a value. Okay, some of you have some problems calculating. Just make sure you have put in the correct units. Okay, pressure is in Pascal. Okay, 1 atm. They did 1 atm. Pressure taken. Yeah, one atmosphere is 1 atm. This is 1 atm, but of course it's in Pascal. Okay, change to meter cube. Cm cube change to meter cube. You times 10 to power of minus 6. Can? Yeah. So mass over mR times 8.31 times the temperature. Temperature in Kelvin, please, plus 273. You should get 36.5. Can? Yeah, it's all mathematics, so they just put in the correct value. Alright? Maybe some of you, the conversion, you didn't get it. That's why you didn't get the answer. So you're actually calculating this MR here. Mass over MR is the most. Alright, okay, so the thing is this. They say, why is the MR value obtained different from the theoretical? Theoretical is 32. You calculated was 36.5. So the reason is this. Because this is called the ideal gas equation. Don't forget, this is called the ideal gas equation. Alright, this is called the ideal gas equation. So once you use this equation, you have naturally made some assumptions. Okay, once you use this equation, you have made assumptions that the gases have what? Negligible intermolecular force, IMF, as also negligible volume. So once you use this equation, this assumption, you have made it already. Okay, so if you look at methanol, right? Methanol here, I just draw methanol. So methanol, we're going to look at the intermolecular. What kind of intermolecular does methanol have? What's this I'm drawing? Yeah, H bond, hydrogen bond. I'm looking for H bond. So the thing is this, so this methanol, does it have negligible intermolecular? It doesn't, right? Yeah. So which means actually when you use this formula, your assumption was wrong already. Okay? So if your assumption is wrong, of course the answer will not be the same as this, isn't it? Yeah, because your assumption was negligible, but the fact that it doesn't have negligible intermolecular, that's all. So methanol vapor does not behave like an ideal gas, right? So using that formula is not 100% correct, because as there's considerable hydrogen bonds between the molecules. Okay, make sense? Yeah, so if you use that formula, you can get 32 provided that gas has negligible intermolecular. I guess hydrogen this type will be quite close, right? Yeah, hydrogen, all this, which it has negligible, almost negligible intermolecular. I guess that'd be quite close. Okay, now let's look at this one. Okay, so this type of questions are quite common for gas as a gas question. Okay, this is also another common question for a gas question. All right, they say the next one. You all copy already? Okay, the next one they say by experiment. So this is the actual volume of the carbon dioxide. This is the actual volume of the space occupied by the carbon dioxide. Okay, then they say what is the volume that the ideal gas equation predicts. So we're going to use the ideal gas equation to calculate the volume. Alright, use the ideal gas equation to calculate the volume. So use PV nRT Alright, so sub in the value for P, sub in for N and R and T, and then find out V. Okay, so don't use this V. Don't use this V. You sub in everything else but that V. Okay, let's see what you get. So you multiply this is the pressure. The pressure is you use the pressure. The volume you don't know, so let it be V. The moles is 1 mole, yeah. So this N 1 mole. R temperature they give you in terms. So yeah, they give you in Kelvin really. That's fine. Okay, so this is the temperature. Okay, then your V is this. Okay, now how do you explain? They say comment on the difference. So the difference between these two, right? The difference is this value is actually smaller. Okay, that's what they want you to notice. And this value is larger. Okay, so the question is, why is the actual volume smaller? Why do you think the actual volume is smaller compared to the ideal gas one? Why do you think the actual volume is really smaller? Why the volume is actually smaller? Because is carbon dioxide an ideal gas? It's not, right? So carbon dioxide is a non-ideal. So what does it have? It has significant what? Intermolecular force. So when something has significant intermoleculars, the volume should be smaller or larger? Smaller, yes, because the attractive forces will pull the molecules closer and then it becomes smaller. So that's what you have to write down. Okay, so what they're looking at. Okay, carbon dioxide are held closer by the intermolecular ID because it's non-polar. So the actual volume will turn out to be smaller than predicted by the ideal gas. Okay, so you even have to compare why smaller, right? Why smaller? So why smaller then is because of the significant intermolecular ID. Pull the molecules closer, the volume will be smaller. So actual volume turns out to be smaller. It's okay? Yeah. This type of question quite popular. Trust me, you might see in your school paper, okay? Yeah, they ask you to compare the differences. Why one big, one small. Right? So that's one of the main reasons. Let's run through this next one. Okay, we're going to apply Dalton's law. So Dalton's law, just one formula. They say in a mixture of non-reacting gases, means the gases don't react, the total pressure is equals to the sum of the partial pressure of all the gases, right? So it means in a container, if there are a few gases like gas A, gas B, gas C, the total pressure will be the summation of all the partial pressure of all the gases. So it's something like this, right? Inside, like say a volume, right? This volume, actually I've got a few gases. So what's partial pressure of A? Partial pressure of A is like gas A bouncing off the walls of the container, right? So when the gas A bounces off the walls of the container, it's constituting a pressure at the walls. Make sense? Yeah. So this is the pressure due to gas A. Then gas B bouncing off the walls of the container. The gas B bouncing off, it gives rise to pressure due to gas B. You add up all the pressure, that's the total pressure. Make sense? Yeah. And the partial pressure, there's a formula that you need to learn. Partial pressure for an individual gas, this is called mole fraction. Actually, it's over there. It's called mole fraction. So mole fraction times total pressure. So what's mole fraction? The number of moles of the gas over the total number of moles of the gas. So very simple. I'm just going to use this example, right? Very, very, very simple. So the total pressure inside here, there are 3 gases, A, B, C. Total pressure is 20 atm. So let's look at the mole fraction of A. So what's the mole fraction of A? Gas A, right? I got 3 moles. But gas B got 2 moles and gas C has 5 moles. So what's the mole fraction of A? 3 out of 10, right? 3 out of 10. So you can see 3 out of 10. This is the mole fraction of gas A, okay? 3 out of 10. Then you multiply by the total pressure. 20 is the total pressure. So 6 atm is the pressure due to gas A. You do the same for gas B, partial pressure. So mole fraction of gas B, right? 2 out of 10. 10 of course here, 5 plus 2 plus 3. So 2 out of 10, mole fraction times total pressure at 4. Okay? So once you add up all of them together, back to square one, you add up all of them together, you get what? 20, which is the total pressure. Okay? So you can actually calculate the individual partial pressure by using mole fraction times total pressure. Alright, so for any time you have to find the total pressure, you just add up the partial pressure, but you must know how to calculate. Okay, let's look at one example. Okay, let's run through this example and then you can do some questions with it. Okay, we're going to apply Dalton's law. Alright, apply Dalton's law as well as Boyle's law. In fact, this one also must apply Boyle's law. So Boyle's law is this one here. If all measurements are made at the same temperature, we're going to use Boyle's law. So Boyle's law, we learned that if the temperature remains the same, right? So let's go back to Boyle's law. If at same temperature, at constant temperature, we can apply this formula. P1 V1 equals to P2 V2. Okay, we're going to apply this one in this example. Okay, very easy. I'm going to just show you very quickly. All right. So over here, what it means is this. All right. I have two gases. Sorry, I have two gases here. One gas X and gas Y. So this small spacecraft, 10 meter cube. This is a spacecraft over here. The volume is quite small, 10. Okay, this is 10 meter cube. Connected to another that's 30. Okay, so this is gas Y, this is gas X. Okay? I just like allocate with different colors. The pressure due to gas X inside here is 50. Pressure due to gas Y is 100. So this is the initial pressure and the initial volume for gas X. So after that, they say you open up, all right? They open up before connection. Then after that, if all the measurement is what is the pressure after connection? After connection means you take away this thing. You take it away. So this is what it looks like now. So gas X now, gas X is not confined to 10 cm cube. Now gas X can move everywhere. So gas X is now the volume for gas X is actually how much? It's actually 40 already, right? 30 plus 10. Okay, can go anywhere. So what we need to do is we're going to apply this formula. We have to do it gas by gas. Okay, we have to do it gas by gas. So inside here, there's gas X. Inside this here also got gas Y, right? So if you add them up, you can find out the total pressure. Okay, we want that, right? So we do it this way. P1 V1 equals P2 V2. Pressure, initial. These are all the initial. This is the final after connection. So initial pressure, initial volume equals to final pressure, but final pressure due to gas X only. So final pressure, okay, final pressure of gas X inside here. All right, but the volume is not 30 or 10. It's actually 40 now. Okay, so you can calculate the pressure due to what? Gas X. Do the same for Y lah. Okay, do the same for Y. So once you do that, they just add them up. Okay, and then you get the total pressure. Make sense? Right, but you have to do the gases individually, right? Initial and final, but for the individual gases, then you add them up. Okay, so this part, the adding up, is actually applying Dalton's law. Right? Okay, let's try the example. I hope you can do it. Unless you can't do the first one, then I'll come in and help you, okay? So oxygen, very quickly, this is the picture. Oxygen here, nitrogen here, all squeezed into a container that is a 2.5 dm cube. So we're just going to use the formula P1V1 equals to P2V2. Alright, for oxygen and nitrogen separately. So I'm just going to print the value very quickly. 200 times 5, okay? This is the final pressure of oxygen, right? Final pressure oxygen. The volume is 2.5, okay? 2.5. So I think pressure oxygen is 400, okay? 400 kilopascal. For nitrogen, let me see, the pressure is 500. The volume is 2. So pressure, which I want to find out, alright? The volume is 2.5. So pressure due to nitrogen, if you bring across, you also get 400, okay? Yeah, so I guess 400 plus 400, that gives you 800. Okay, so very good. I think most of you got D. Okay, this next one here basically is more similar to the example that we did just now, where they connected, right? So this one very quickly, helium, I just do helium. Pressure 2, volume 1. Okay, partial pressure of helium, I don't know, but the volume is when they are connected. So when they're connected, the total volume is 1 plus 2, right? Yeah, so it's 3 dm cube, right? So pressure of helium now would be 2/3, okay, 2/3 kilopascal, yes, on kilopascal. So this one here, very quickly, P1, okay, P1 for neon, right? What's the pressure? Neon is 1, volume is 2. So this one I don't know, but final volume after connection is 3. Oh, so same, so this one also 2/3. Okay, so add them together, total is actually 2/3, 2/3 is 4/3. Alright, so I think it's quite obvious, right? This one is A. Make sense? Okay, let's try this third one. This one is the A-level question that I think some of you maybe had a bit of problem doing. Not too difficult, but let's see how it's done. Okay, PV equals to nRT. I'm going to just do it for hydrogen. Okay, they say 2 grams sample hydrogen. Alright, blah blah blah, temperature T, volume exerts a pressure P. Which of the following will exert a pressure P at the same temperature? So I'm going to find out what's P first. P equals to nRT over V. Okay, what's the number moles of hydrogen? We're looking at hydrogen. 2 grams, right? So 2 divided by 2 is 1. Is okay? Yeah, 2 grams of hydrogen means 1 mole. Okay, so because 2 divided by 2 lah, MR of hydrogen is 2. Hydrogen must take it as H2. It's okay? Take H2. So the MR is 2. R times T over V. So actually it's RT over V. So which of the following will exert a pressure P at the same temperature? Which means which one of them the P will also be RT over V. That's all. Okay, so just check. So I'm just going to do two examples. Then I'll show you. Just do two examples. One right, one wrong. Okay. So if I did for B. Okay, see, now we're doing B. So for B, let's try P equals to nRT over V first. Okay, what's the number of moles of deuterium? 4 grams of deuterium is 4 divided by what? What's the mass of deuterium? This deuterium. What's the mass of deuterium? You can't use 2 because deuterium, when we say hydrogen, we say H2. When we say deuterium means it's D2. It's okay? Yeah, so it's 4. You must use 4. Okay? It's just a hydrogen, you must use 2. Here you must use 4 because the mass number is 2. So here must use 4. Are you me? Yeah, because you have to assume it's D2. You can't assume it's D. It exists as a diatomic. Makes sense? A hydrogen. Okay, so this 4 over 4. Does it make sense? Yeah, it's 4. This one is 4. It's not 2. So R times T. Let's see. T is the same temperature, right? But volume is V over 2. So in fact, this one ends up be 2RT over V, which is not the same as RT over V. Okay? Cross out. Okay, we'll do the next one. P equals to, I'm doing C now, nRT over V. So number of moles of the gas, 1 gram of hydrogen is 1 over 2. 2 grams of deuterium is 2 over 4. So this is the total number of moles of gas. Are you me? Yeah, then R, temperature T, nice. Volume is still V only. That's the answer already. Because this is RT over V. So no difference from the beginning. There was a gaseous mixture occupies this volume, and then they say contains a mixture of this one, Cl2 and Cl2, right? So the MR for this one is actually 70, okay? And the MR for this one is actually 74, correct? That's why you will see here is 70 and 74. Make sense? Yeah. So which means some of them are 70, some of them are 74. So we want to find out what's the average, right? So you can use PV nRT. I hope you managed to get the answer with using PV nRT. So let's check. PV nRT, you plug everything in, right? Your answer should be about 71. Okay, so pressure change, no, ATM changed to Pascal, right? So to change to Pascal, normally I times 1.101325. Okay, ATM change to Pascal. Volume is in dm cube. Please change to meter cube. To change to meter cube times 10 to the power minus 3. Okay, check because maybe some of you have always conversion problems. So you don't convert properly, you don't get an answer. So everything else is fine already. So average MR should be about 70. Okay, it's actually like that. You add up the X and Y are actually the mole fraction. Okay, X and Y are the mole fraction. So you add up the mole fraction, it will always be equals to 1. Okay, you add up the mole fraction, always be equals to 1. So you can see that the average MR already calculated was 71. So 71 equals to 70x plus 74y. So all you need to do is this, like y, what's y? So y is equals to 1 minus x. I told you solve simultaneous, right? So y change to 1 minus x. Okay, so you can just solve for x and then you're done already. Okay, so solve for x. Okay, let's try. If you solve it, I'm doing the same thing. Okay, just solve for x. So you turn out the value for x is 0.75, and if x is 0.7, y is 0.25. Okay, then you can calculate the partial pressure. So the partial pressure of 35 Cl2, right? Partial pressure of 35 Cl2 is equals to the mole fraction times the total pressure. So mole fraction is x. So mole fraction is x 0.75 times the total pressure, which is 1.2 atm. Done already. Okay, so it wasn't that difficult. I think some of you struggle with understanding that you're supposed to solve simultaneous, right? Okay, so the value, let's check. So 0.75 times 1.2, 0.9, and then that one is 0.3. Okay, it's actually solving simultaneous. This is exactly like A level, the way they did it. But I think it confused students. I don't know why. Yeah, it's okay. Okay, I guess everybody should have gotten 55.8. So I think that one is fine. Okay, it's okay, you should get 55.8. It's okay? Everybody got that? Alright, okay. So the only thing that I would say is this. So you have to look at what the reaction, right? So they say F2 plus NaOH produces NaF and a triatomic gas. So what's a triatomic gas? So the thing is this, you only have a few elements to play with. You know, you only have NaOH and F right? So you don't have much elements to play with. So, but since it's also simple molecular, it's a gas, I believe you can use O, H, and F. Yeah. So F is 19, O is 16, and H is 1. Yeah. So triatomic means 3 atoms in a molecule. 3 atoms in a molecule. So which means I give you a few options. It could be O3, it could be F3, right? I think some of you were thinking of that. Okay, if I use O3, it's 48, a bit far lah, right? A bit far from that. If I use F3, it will be 19 times 3, it will be 50, what? 50, how much? 57, is it? I mean, F is 19, right? Yeah, so 57. So it looks as if it's possible. Can you draw F3 possible? Can you ever draw F3? You can never draw F3. Why? Because if I try to draw F3, it's like that. See, yeah? F3, right? So imagine single bond, then 1, 2, 3, 4, 5, 6, 7. Correct? But is it possible? No, because F has how many electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9. F is in period 2, cannot expand octet, right? So if you try to do F3, impossible, 100% impossible. So the only answer, actually, think about it, I'll not use H at all. H1, how to get triatomic and hit 55.8. Cannot use hydrogen. So the best answer turns out to be F2O. Okay, F2O turns out to the best answer. In fact, F2O, if you add together, what's MR? F2O. F2O is how much? 16. Tell me, how much? 16 plus 19 times 2. 50 what? 54. Oh, okay lah, quite close like this, and this one makes sense. So F2O is actually drawn like that. If you want to try to draw F2, it looks like water. Okay, it's actually F2 and it's totally feasible. Okay, yeah, I mean you have to try and error lah. There's no other way. So a lot of students put F3, which is wrong. O3 too small. This is the best answer. Okay, this is the best answer. Alright, but there's a reason why this can be formed lah, but never mind, I won't go into detail. Okay, now the last part. Explain why there's a difference between the theoretical MR and that calculated. So the theoretical MR is this one here, and the value calculated, this is a value calculated, sorry, this is a value calculated, but the theoretical MR is 54. So they're trying to say, why is there a difference? Why is there a difference? So again, the same concept. Once you use PV nRT, you're assuming what? The gas is what? Ideal, right? So it has negligible intermolecular force attraction. Then you look at F2O. F2O is the polar or non-polar molecule. Polar, good. So I have to draw the dipole moments this way. So there's a net dipole moment pointing down. It is polar. Please mention that it has ID, ID, and PD, PD. Okay, so it has still some significant intermolecular. Alright, so the value would not be the same. Okay, standard question. So if you as long as you use PV nRT, you assume it is negligible already. Yeah, so that's the standard thing that you should write down. Okay, PD, PD, and I think maybe it's good that an ID lah, put plus an ID, and it's not negligible. Okay, so this is a polar molecule. Okay, all right. Okay, let's move on to the next one. Okay, next one is more of to do this next question. Actually, normally I don't like to do this type of question, but sometimes you see this type of question, and it appears for A level. Okay, it does appear for A level. Not recently, but quite a few years back. Okay, this type of question that comes out, and some students get totally confused what is happening. Okay, and you can see your school paper. Sometimes you throw this type of question again. All right, so let's see. Is it okay? The previous question. Right, this one, a sample of m grams of organic compound vaporized in a gas range occupies the volume, temperature, and pressure. So if I did PV equals to nRT, okay, let's try. PV equals to nRT, PV equals to mass over mR, RT, which means mR, let's do some mathematics, mRT over PV. So if I try to throw everything in, like mass is m, R is R, temperature, temperature, so they give you T. Okay, pressure is P bar, so I'm going to change it to Pascal, P times 10 to the power 5. Volume is in cm cube, so I'm going to change it to dm cube times V over 10 to the power minus 6. I mean, yeah, so this is how I do it. Okay, then after I load my options, and my options are totally not the same as this. Okay, yeah. So if you look at all the options given, right? Firstly, I don't see a R. My answer has a R, but here I don't see any R. Then after that, we also can see that something turned out, which is not even a question. So where do you think you see the 22700? This, what's that? STP, right? 22.7 dm cube. So we need to actually manipulate it such that we can get one of the options. So in order to do that, we're going to use STP. So that's how we do it. Okay, so this is the working to show how it is done. Alright, so we're going to use an STP first. So we're going to do two equations. One is the STP and one is for the gas. So STP we learn is 1 bar. Volume is 22.7 dm cube. But I'm changing to cm cube. Why? Because I see this in the option, right? I'm trying to fit the answer in the MCQ. Alright, so I have to change it to cm cube. 1 mole of gas R, and this is actually 0 degrees Celsius, so it's 273 Kelvin. I do for the gas also, and the gas I use P bar. So actually pressure I want this bar, that's why here also bar, okay? Yeah, and the question also gave you bar. So volume is cm cube, see, same unit, yeah. Mass M over mr, R and T. Okay, and then what happens when you do 1 divided by 2? So when you take 1 divided by 2, equation 1 divided by equation 2, you notice few things can cancel, R can cancel out, right? You manipulate, you get answer already. Alright, as much as actually this question, very little concept, is how you learn how to manipulate. Okay, and do you know why they want to do that? You know one reason why they want to do that? Because if you use only PV NRT, right? You know something, if you use PV NRT, right, you are actually 100% assuming that it is what gas? Ideal gas. But if you try to incorporate STP, right, when you do STP, right, is it an ideal gas or real gas? It's actually a real gas, right? Are you me? Yeah, STP. At STP, when all gases occupy 22.7 dm cube for 1 mole of gas, right? So the STP is a real gas. So when you put them together, your answer is more accurate. Yeah, I wrote down everything over here already. If you want, you can look at it. But you just have to manipulate such that you can find the mass. Yeah. PV, okay, for RTP, PV equals to N is 1 mole gas, R times T, can? Okay, but now we're looking at oxygen. Oxygen, what did they give you? They give you the pressure, 1 atm. Volume, I changed to dm cube. The reason why, because the option shows me everything is in dm cube, okay? Yeah, so I change it to dm cube. So 75 cm cube, I change it to dm cube. Mass over mr. Oxygen is 32, because here is O2, right? So mr is 32. R, then the temperature is just this. Okay, you just do some manipulation, you can get answer. Okay, can I do the working for this one already? I already did nicely for you. Okay, let's just use 1 over 2 lah. Okay, if you can't see that, we'll just do together. 1 over 2, right? Cancel. Left behind is 24 over 0.075. Okay, on the other side, I think the R can cancel, right? So on top is actually 293 divided by mass over 32. Okay, because I don't like to put 32 below, I'm going to put the 32 on top. Is it okay? Yeah, I think not the correct. That's 32, don't put below, put on top. Okay, then what else? Divide by 423, right? 423. Okay, that's all. Okay, you can get an answer already. So let's see here. Mass is equals to, bring across. So mass equals to 293 times 32 times 0.075. Bring across down here, 24 times 423. Yes, that's the one, right? A. Can? Yeah, work it out. So it's a bit of I mean, it's really manipulation, okay? You might find such questions. Is it okay? No concept, right? Just maths. Yeah, just maths. Yeah, manipulation. Okay, let's run through the next one. Okay, next question. I want you to calculate the MR and then decide how you're going to draw the molecule. So this one, if you did very nicely, PV NRT, right? You change, let me see, what did they give you? Pascal, so it's okay. Pascal volume, let me see, volume is 10 dm cube, change to meter cube, so divide by 1000, okay? Divide by 1000, you get it, So MR, okay, so you can calculate MR is actually 263. So I think you probably know that aluminum chloride, okay, it's AlCl3. So aluminum chloride, what's the AR of aluminum? 27, is it? Is it 27? Yeah, I think remember it was like 27. Okay, so actually the MR for this guy, right, for aluminum chloride is actually 27 plus 35.5 times 3. That is equals to 133.5, can? Yeah, 133.5. So 133.5. So I guess if you times 2, it's almost double, right? It's 267. But I mean, this is all calculation, assuming it's ideal gas. you won't get 100% 267. So this is almost double, it's good enough. You say it forms a dimer, okay? It forms a dimer. So theoretically, you should actually draw this, okay? Draw this. So aluminum chloride, I mean, that's how you draw it. Cl, okay, maybe just highlight lah. I won't draw it out yet. Okay, but you must be able to draw aluminum chloride. This one aluminum chloride. This is another aluminum chloride. Then draw dative bond. The dative bonds the electrons come from the Cl. Okay, electrons come from the Cl, dative bond, electrons from Cl, dative bond here, okay? And then aluminum will be stable because it has now 8 electrons. Okay, so this question is about dimer. Okay, how do you think look at the part 2. As the temperature is raised, how will you expect average MR to change? Increase or decrease? Will the average MR increase or decrease when the temperature is raised? So by raising the temperature for Al, Cl, now you have Al 2, Cl6, right? So when you raise the temperature, basically the heat will be used to break bonds, right? The heat will be used to break bonds. So you're going to break bonds, and then what do you think is the most logical product? It will go back to AlCl3. Yes, it's going to break bonds and go back to your aluminum chloride. Yeah, because heat will always break bonds. So if that's the case, what can I say about the average MR? Will it increase or decrease? It will decrease, right? Because this is a big molecule. Now you get small molecules, okay? So basically the MR is going to drop. So tell me the average MR should decrease as it forms back AlCl3. Okay, so it becomes a big molecule. So heat usually will break bonds, so I guess that's the concept. Yeah. Okay, let's look at the next one. Next one is also pretty similar. Okay, pretty similar in terms of what you're supposed to do. Okay, pretty similar in terms of what you're supposed to do. So I think if you did your calculation using PV NRT, you should get these values. All right, MR will be 120 Okay, you did it nicely. So if you try to calculate the MR of ethanoic acid, ethanoic acid MR is actually 60. Good. So I guess the concept is the same, right? Dimer. Okay, but the problem is I know some of you have problem drawing ethanoic acid and its dimer. Okay, so maybe very quickly I just want to show you, instead of just giving you the answer, I want you to think this way. So I'm just going to show you how I will attempt to draw it. Okay, so you must know how ethanoic acid looks like first before even you can do it. So firstly, ethanoic acid looks like this, CH3. Okay, I'll draw the full thing, okay, just to show you. Okay, the full thing is like CH3, alright. Okay, this COH, right, is like that. C double bond O, OH. Okay, you know why I draw this way? The reason why I draw this way, what's the shape of this carbon? Really, what's the shape of this carbon? 3 bond pairs, no lone pair. What's the shape? Trigonal planar. Yeah, I'm trying to draw trigonal planar with me. Then you look at the OH. Am I not drawing the proper way? I'm trying to draw what shape is this? What shape about the O? It's bands actually. See? So you have to draw it this way, then everything will make total sense. So I'm going to draw the other one, exactly the same. Okay, but so you need to, about this carbon, you have to draw trigonal planar, right? So trigonal planar, but now the O instead of on top, now I put it below, and this is OH. So you can see the structure is pretty nice, right? Pretty nice. So I guess you know what's going to form here, right? This will be what? This will be your hydrogen bond. Okay, so please learn how to draw this properly, okay? So I'm trying to show you when you do this, you have to draw the correct shape and things will really make sense. Not anyhow draw. Alright, so when you draw it out, please understand that's what I'm driving at. Okay, so yep, so you have hydrogen bonds. So in terms of a marking point for hydrogen bonds, I'm going to tell you exactly what we are going to mark for your school or whatever. We'll mark for this. I want to see the lone pair on the O, on this O. I want to see a delta plus on the H and a delta minus on this O, okay? The OH bond, you must show delta plus, delta minus. The H is delta plus because of the O. So it's good to show delta plus, delta minus. And then show also the lone pair on the O. Then that's fine. Okay, if you want a bit more, you can just put delta minus on this O. But as long as you show the lone pair, we are okay with. Okay, that's the purpose of drawing a hydrogen bond. Make sense? Okay, so yeah, exactly. I think this one I should put a delta minus here. Okay, then it makes sense. So the shape, the way you draw it is important. Okay? Yeah, so if you don't know the shape, then it's hard to draw. We're going to use PV NRT and we create density as one of the variable. So very quickly, PV equals NRT. Okay, so N is actually mass, alright? Sorry, this is mass over the molar mass. So this is actually the molar mass, right? Yeah. So actually we're gonna just bring the V across. Once you bring the V across, there's M over V. and M over V is actually your density. Okay, this is your density. Okay, so we represent density by showing this. Okay, this is it's like this. Okay, so this is density. So yeah, so it's all about manipulation. So sometimes questions can ask you to find out the molar mass or even to find out the density. You just have to play around with it. Okay, so not too difficult. So you can see from this expression, right? You can just look at this expression very quickly. So you can see that when temperature rises, all you need to know is when temperature rises, density, what happens to density? Density actually decreases, right? When temperature rises, then density decreases. That's why we say hot air rises, right? So when temperature rises, right, the density drop. Okay, density drop. That's why the hot air will actually rise. Make sense? Yeah. So the opposite is of course true, lah. So if the temperature decreases, the density will increase. So density increase, that's why cold air will actually sink, right? So that's a very, very simple concept. I mean, because you're talking about gases. Okay, so with that, I want you to try to sketch the three graphs, right? The three graphs. Try to sketch the three graphs. It's actually it's a pressure over density. It's not very clear, but actually it's supposed to be pressure over density for the next two. Pressure over density. Okay. So try to sketch it. Okay, notice I'm just going to use this formula, right? Pressure is equals to density RT over M. Okay, because I've already proven this already. So very quickly, I'll write it over here. So pressure is equals to density RT over M. So what you're trying to plot is actually pressure versus density. So look over here, R is a constant, and it told you constant temperature constant. The molar mass for a certain gas is also a constant, which means this entire thing is actually a constant. Okay, so which means pressure and density are proportional. So you're supposed to draw a straight line up. Okay, so draw a straight line up as proportional, okay? And the gradient is of course is RT over M. That's a gradient. Okay, so you must be able to understand and do it this way. Right, pressure is proportional to density. This whole part is a constant. Okay, the next one, pressure over density versus pressure. So pressure over density is equals to RT over M. Okay, so I'm looking at pressure over density here. See, pressure over density, right? So let's look at what is constant. R is a constant, temperature is constant, and molar mass of a gas is always a constant, which means this entire thing is actually a constant, isn't it? Yeah. So your graph should just be a straight line, horizontal straight line. And the value here is RT over M. Okay, because it's a constant, doesn't change. Right? Okay, last part here. Pressure over density versus temperature. So let's look at the same thing. Pressure over density equals to Rm over times T. Okay, so now you're plotting pressure over density versus temperature, okay? Yeah. So R is a constant, M is a constant, which means this is your gradient, isn't it? Yeah, so actually it's supposed to look like that. Okay, but I'll say this, it's supposed to look like that, but you're not going to draw this because temperature, if you draw like that, temperature is in Kelvin. But now temperature is not in Kelvin, temperature is in degrees Celsius, I mean. So you change it to degrees Celsius. So how do you draw it then if it is in degrees Celsius? So maybe, let me just move this away. Sorry, just move this away, yeah? So this one's just a straight line. Okay, so over here, let's see how am I supposed to draw it. So pressure over density is equals to R over M. This is just a quick proof. Okay, say T, this T is in, say this T is in degrees Celsius. So T is in degrees, this T is actually in degrees Celsius. I'm going to change to Kelvin, I must plus 273. Alright, so mathematically we know that the x-axis is when this guy is 0. This guy is 0 means it's the x-axis, isn't it? Right, x-axis. So x-axis, when it's 0, T must be equal to minus 273. So which means minus 273, right? Okay, so it should be like that, scale to that side. Okay, so this is what the graph should look like. So I'm just going to erase this. So it should actually be along this line, and then it will actually try to cut at minus 273. Make sense? Yeah, so that's how it can be proven easily. So nitrogen, don't forget, I think some of you totally forgot. Nitrogen, actually the MR is actually 28. Okay, not 14. Okay, 14 is only for N. So nitrogen MR is actually 28. So you can see your numbers have been doubled or something like that. Okay, so I'm going to just use a formula that I just we did already. So density is pressure times molar mass R times P. So pressure here, I think at room temperature and pressure is 1 atm and 20 degrees Celsius, right? So 1 atm is 101.325 Pascal. So use this value. So this 1 atm in terms of Pascal, molar mass is 28, R is 8.31, and temperature is in Kelvin. So plus 273. Check, you get 1165, actually it's gram per meter cube. So far when we did this, when we did this, notice over here, density is mass over volume, right? But mass was actually grams, and volume is always in the SI unit, which is actually meter cube. Okay, so you need to know that this volume here originally was really meter cube. Okay, so it's actually grams per meter cube. So your density is grams per meter cube. So we got to convert it to what, grams per cm cube, right? So it's actually not that difficult. Let's see how I normally do it. So if maybe some of you know how to do, but this is normally what I do. If I want to convert to cm cube, right? So what I do is this: I put on top as meter cube and below as cm cube. So why I do that? Because the meter cube and the meter cube can cancel out. All right, and then you notice, I'll write this: 1 meter cube is 10 to the power of 6 cm cube. That's it. So that's the answer. Does it make sense? Yeah, so I just do some simple conversion. I mean, okay, so that's done. Okay, so the next one, this question, all right, the learning point is this. They say this nitrogen, and then this is pure nitrogen. This one is nitrogen with something else. This is N2 plus another gas, right? Another gas, and this actually is pure nitrogen. So actually, this question doesn't need any calculation at all. So you don't have to use PV, NRT, anything of that sort. You can see that this density is greater than this one here. So what they're trying to tell you is, because this density is greater than this nitrogen is contaminated with a what? A heavier or lighter gas? Heavier gas, that's all. Okay? The density is greater means is with a heavier gas. I mean, so then you check out all the MR for everything, all of them. You check the MR for all of them. You realize the one that's heavier than nitrogen. Nitrogen is 28. So the one that's heavier than nitrogen is actually argon. Right, so the answer is argon. All the rest are lighter than nitrogen. All the rest are lighter than nitrogen. I mean, yeah, so pick the one that is heavier than nitrogen. Okay, this was actually a very popular 11 question. It came out a few times. Right, this one I don't think I need to go through because we did the graph just now. So this one answer is just B. Okay, that's what we did just now. The temperature was in degrees Celsius, that's why it's B. Okay, degrees Celsius. Okay, this one I think is quite well done. I think most of you got D, but that's the correct answer. But for those of you who didn't manage to do it, this is how I'm going to show you. So pressure is density RT over M. It was proven already. So I'm not going to redo it. Okay, so pressure for E, just put density RT over M. Okay, then look at D. The density of gas D is twice that of gas E. So I'm going to put down twice, right? So 2 density, okay? Twice. And the molecular mass of D is half that of gas E. So I'll put RT over half of gas E, right? So I'll put half M, okay? So just simplify, really you get 4:1, okay? Just simplify. Because 2 over half is 4 already. Everything else will just cancel out. Make sense? Yeah, so that's how you do it. Okay, let's try this one. This is a bit tricky. So I guess density, we proven density has this formula. Let's try it. I always like to refer. Density is PM over RT. Okay, PM over RT. So density is actually PM over RT. Okay, and you look over here. What's the pressure? Pressure is in terms of bar, P bar. This is bar. Okay, never mind. Just write bar first. Then the MR, the molar mass is also M. See, given. So this R and this is T, and temperature also to give you a T. Alright, so this is what you should be looking out for. But if you look at it carefully, you can't get the answer because all of them don't have R and all of them have this value, right? 22700, and then all also have 273. So this is what you need to do, and then you can actually sub inside. So where did all these values come from? All these values came from where? Came from STP. Okay, STP. So STP, think through STP, if I use PV equals to nRT, right? So I'm going to keep the units exactly the same. So STP actually, remember, is actually 1 bar. So 1 bar is 22.7 dm cubed. Okay, and it's 0 degrees Celsius, which is 273 Kelvin. Okay, so I'm gonna use the same concept. So because I'm using bar here, so this one will be 1 bar. That's why I have to change it to 1 bar. So this is 1. SDP is 1 bar. Volume, this volume here, let me see. Oh, volume here is in what? cm cube, right? Volume here is in cm cube. So I have to use this volume also in cm cube. So 22700 cm cube. Okay, so this is bar, this is cm cube. Just make the units all consistent. N is of course 1, R is R, and T is 0 degrees Celsius, which is 273. Okay, so you notice something, I can just play around a bit. So R will be equals to what? R is equals to 22700 over 273, okay? Yeah. So what you do to this value, take this value and then sub inside here, and then you see the answer. Okay? So it's a bit tricky because they put all these numbers, so you have to use the STP to do it. So this is probably the way I will do it. So P times M, then over what? R is this, right? So it's a 22700 times T. The 273 bring up, yeah, so 273. Okay? So that means the answer will be B. Maybe? Okay?